Let us now discuss the next topic in the chapter of circles, and we are going to discuss today in this video the angle subtended by an arc of a circle. So if you look at this diagram here, we have a circle and we have a certain angle subtended at the center by an arc of the circle. So we have an arc PQ of the circle subtending a certain angle POQ at the center of the circle. Now we have to distinguish between two arcs. The smaller segment of the circle is called as the minor arc. So if you look at this arc PQ, it is smaller compared to the other arc on the other side, which is much bigger. So the bigger arc is called as the major arc and the smaller arc is called as the minor arc. So the angle POQ, which is the black angle shown here, is the angle subtended by the minor arc at the center of the circle. Similarly, the angle subtended by the major arc is the reflex angle POQ. So reflex angle POQ, which is marked by the red angle over here, that denotes the angle subtended at the center by the major arc of the circle. Okay, so we need to have a clear understanding of what is the angle subtended by the minor arc and major arc. So angle POQ, shown in black here, is the angle subtended by the minor arc PQ, and the reflex angle POQ is the angle subtended by the major arc PQ. Next, let us look at a theorem regarding the angle subtended at the center and the angle subtended at any other point on the circle. Just as we had for the chords, the same thing applies here as well for arcs. The angle subtended by an arc at the center is twice the angle subtended by the arc at any other part on the circle. So we have the first case where we take the angle subtended at the center by the minor arc. So we have this PQ over here, which is our minor arc. It subtends an angle POQ at the center. So that's our angle over here, angle POQ. And what the theorem states is that the angle subtended at the center, that is POQ, is 2 times the angle subtended at any other point on the remaining part of the circle. That means this we can have some point A on the remaining part of the circle, and the angle subtended by the minor arc at any other point on the major arc will be half the angle subtended at the center. And conversely, we can say that the angle subtended at the center is 2 times the angle subtended at any other point on the circle. So this point A could have been at any other place on the major arc. So it's I marked it here. It could have been somewhere here or here or here. Wherever it is, the angle subtended at the center is going to be 2 times the angle subtended at any other point on the remaining part of the circle. Now to prove this, let us consider this diagram where we have a circle with an angle subtended at the center, which is angle POQ. And we need to prove that this angle POQ is 2 times the angle PAQ. So to prove this, we are going to join AO and extend it to some point B inside the circle. And after that, we will apply some rules from triangles to prove that the angle subtended at the center is twice the angle subtended at any other point on the circle. So we have joined AO and extended it to some point B inside the circle. Now if we look at the angle BOQ, which is going to be this angle here, marked in black, the angle BOQ is going to be the sum of the angle OAQ, which is this, plus the angle OQA, which is this. Okay, and that comes from the rule of the triangle, that the external angle of the triangle is the sum of the two interior angles on the opposite side. So the external angle here, which is BOQ, is equal to the OAQ, which is this angle, plus OBQ, which is this angle. Okay, so that's our first observation based on the rules of the external angle on the triangle. So we have that angle BOQ is angle OAQ plus angle OQA. It's this plus this equals this. But we notice that OA and OQ are both radii of the circle. So we have in this triangle OAQ, OA is equal to OQ. So that means the triangle OAQ is an isosceles triangle. And if it's an isosceles triangle, the angles opposite to the equal sides are also equal. That means OAQ is equal to OQA. So therefore, we can write that angle OAQ is equal to angle OQA, and therefore we can write angle BOQ is equal to angle OAQ plus angle OAQ, because OQA is equal to OAQ, so that means it is 2 times angle OAQ. So the first observation we have is that the angle BOQ is 2 times the angle OAQ. So we have already shown that angle BOQ is equal to 2 times angle OAQ. That means this angle over here is 2 times the angle over here. Okay, and similarly we can also show that the angle on the other side here, which is this angle, is also 2 times of this angle. We can show that by seeing the angle BOP is equal to angle OAP plus angle OPA. But again, as before, we have OA is equal to OP, being the radius of the circle. So OA equals OP because they are radii, and therefore we will have angle OAP, that's OAP, is equal to angle OPA. Why? Because we will have angle OAP as an isosceles triangle with OA is equal to OP, and therefore the opposite angles will be equal. So therefore OAP, angle OAP and angle OPA are same. So therefore we can write angle BOP as angle OAP plus angle OAP, that is 2 times angle OAP. So we have shown now the angle BOQ is 2 times OAQ, and similarly the angle BOP, which is this one, is 2 times angle OAP. Now we can see what is the angle POQ. So angle POQ is nothing but the angle BOQ plus the angle BOP. So we have already angle BOQ is nothing but 2 times angle OAQ, which we already have shown over here, and then we have angle BOP, which is equal to 2 times angle OAP. So we get that as 2 times angle OAQ plus angle OAP. But what is angle OAQ plus OAP? It is the sum of these two. OAQ is this one and OAP is this one. So the sum of these two is equal to the total angle over here, which is nothing but the angle PAQ. So that gives us to be 2 times angle PAQ, which is what we had to prove. That is angle POQ, which is the angle subtended by the arc at the center, which is angle POQ, is equal to 2 times the angle subtended by the arc at any other point on the circle, which is the angle PAQ. So we have shown that angle POQ, which is this angle over here, is equal to the angle twice the angle PAQ. So the angle subtended at the center is double the angle subtended at any point on the remaining part of the circle. We have proved this for the first case, where we have taken the angle subtended by the minor arc. So PQ is the smaller of the two arcs, So we have taken the center angle as the angle subtended by the minor arc. Similarly, we have taken the angle subtended on the circumference also as the angle subtended by the minor arc PQ. Okay. Next, we will take the case when the minor arc and major arc are both of equal length. That is when we have a semicircle, the angle subtended by the semicircle. So we have here in this diagram representing the second case where the arc PQ is a semicircle. So that means the major arc and minor arc are of the same length. So that means we are trying to find what is the angle subtended by the semicircle at the center and at one of the points on the circumference of the circle. Clearly, if PQ is a semicircle, that means the line PQ here is the diameter of the circle. So the line PQ is a straight line. So the angle subtended by the arc or by the semicircle at the center is this whole angle here on the straight line. So the angle on the straight line POQ is 180 degrees because the angle subtended or the total angle on a straight line is 180 degrees. So the angle subtended at the center by the semicircle PQ is 180 degrees. And from our theorem, we know that the angle subtended at any other point on the circle is half the angle subtended at the center. So half of 180 is 90 degrees. That means the angle PAQ is 90 degrees. So we have these two lines perpendicular to each other. So angle PAQ is 90 degrees and the angle POQ here is 180 degrees. So this is 180 degrees and here we have 90 degrees. So that means angle PAQ is 90 degrees. That means the angle subtended in a semicircle is 90 degrees. So the angle subtended on any point on the circle by a semicircle is 90 degrees. Similarly, if we had a line joining here, that would also be 90 degrees. So the angle subtended by the semicircle is a 90 degree angle. That's our second case. Okay, let's look at the third case where we will consider the angle subtended by the major arc. So we have here the angle subtended by the major arc PQ. So we are going to look at the angle subtended at the center by this major arc PQ. So that is basically going to be the angle on this side here. So that's nothing but the reflex angle POQ, but on the reflex side. So the angle subtended by the major arc PQ, which is this big arc over here, is the reflex angle POQ, and that's the angle subtended at the center. And as per our theorem, the angle subtended at the center is 2 times the angle subtended at any other point on the remaining part of the circle. So PQ is our major arc. The angle subtended by the major arc at the center is the reflex angle POQ, and therefore the angle subtended at any other point on the circle is any point A in this minor arc PQ. So we have A here. So the reflex angle POQ is 2 times the angle PAQ, which is what we have denoted here. Or we can write angle PAQ as angle PAQ to be half of the reflex angle POQ. Reflex angle POQ. So we have discussed the first theorem related to the angle subtended by the arc at the center and the angle subtended by an arc at any other point on the circle. The theorem states that the angle subtended at the center is twice the angle subtended at any other point on the remaining part of the circle. Okay, and we have seen it for 3 different cases. The first case, we took the angle subtended by the minor arc. In the second case, we took the angle subtended by a semicircle. That means both the arcs were of the same length, in which case we got the angle subtended by the semicircle as 90 degrees. And in the third case, we took the angle subtended by the major arc, in which case the angle subtended at the center is the reflex angle POQ, not the angle inside here, but the reflex angle POQ. That should be twice the angle subtended at the circumference of the circle. The next theorem that we will see in this video is related to the angle subtended by the same segment. For example, we have an arc PQ here, that's the minor arc here, PQ. It subtends a certain angle POQ at the center, which is this angle over here, and it subtends a certain angle on the remaining part of the circle, which is this angle here, which is PAQ. Now, the point A on the remaining part of the circle could have been anywhere on the major arc. Okay, we have drawn it over here, but if it was at any other point, either here or here or here, all this constitutes as the angle subtended by the same minor arc or by the same segment of the circle. So the angle subtended by the same segment of the circle are equal. So let's draw that. So if we have another point which we will name as C on the major arc here, that's the angle subtended by the minor arc PQ or by the segment PQ of the circle. So the angle PAQ, which is this angle over here, is the angle subtended on the circle by the segment PQ. But if you notice here, the angle PCQ, which is this part, this angle over here, is also the angle subtended by the same segment of the circle PQ. So that's the angle subtended at some point C on the circle by the same segment or same minor arc PQ of the circle. So what this theorem states is that the angles in the same segment of the circle are equal. So that means angle PCQ is equal to angle PAQ. So both the angles PAQ and PCQ must be half of the angle subtended at the center. So the first observation is that PCQ is equal to PAQ, that's Q here, and both of these should be equal to half of the angle subtended at the center. So angle PCQ should be equal to angle PAQ, and both of these should be equal to half of angle POQ, which is the angle subtended at the center of the circle. So like this, we could have had any point on any part of the major arc. All of those angles would be the same. For example, let's say we had another point D somewhere here. So I'll mark that point as D. So the angle subtended over here is PDQ. That will also be equal to PAQ and PCQ. So angle PDQ is equal to angle PCQ is equal to angle PAQ. So like this, we could have the point on the circle at any point on the major arc. All those angles would be the same because they are all angles lying in the same segment of the circle, which is this minor arc PQ. Okay, we'll stop here and we'll continue with some more theorems in this chapter, and later on we will do some example problems by applying these theorems and solving some numerical examples based on these topics.